The squeeze theorem. This theorem is also known as the sandwich theorem. Sometimes we can't find the limit directly, but we can find it indirectly by using the squeeze theorem. We are going to squeeze the function f between two functions h and g to find their limits. So the way this works is that if I have two functions where one is strictly above, and we'll call that h, and I have one function that's strictly below, and we'll call that g, then if I have a function f that is always between these two functions, then the limit as we approach c is going to be some y value L. So the way this works is that we're saying that if the limit as we approach c for h is L, and if we approach c for g and it's also L, then the function that's bounded in between them has to also be L. So this is the theorem written explicitly. Theorem 4, the squeeze theorem. If g of x is less than or equal to f of x, which is less than or equal to h of x, for all x not equal to c in some interval around c, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x, which is equal to L, then the limit as x approaches c of f of x is equal to L. And again, the reason this works is because if you think about it, if the output of g of x is 5, and the output of h of x is also 5, the only output that is less than or equal to and greater than or equal to 5 is just 5. Now let's see the squeeze theorem in practice. So example 9, using the squeeze theorem. By using the squeeze theorem, we are going to show that the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. So before you even use the squeeze theorem, we're going to see if we can just solve this limit directly. So if I go ahead and plug in 0, I get 0 squared times sine of 1 over 0. So you get 0 times sine of 1 over 0. And this is nothing. We don't know what this is because we don't know what sine of 1 over 0 is. So this doesn't work. So because we can't actually determine the limit, we're going to use the squeeze theorem to help us out. So the way the squeeze theorem works is you need to bound our function between two other functions. So just looking at this piece right here, we notice that x squared we can't really bound. However, we can bound sine of 1 over x. So the function sine of 1 over x is always between two numbers. And sine is always in between -1 and 1. Now if you notice, we almost have everything we want. We just need that last x squared. So what we're going to do is we're going to multiply everything by x squared. And so we get negative x squared is less than or equal to x squared times sine of 1 over x, which is less than or equal to x squared. So if we go back to our theorem, this is our g of x, and this is our h of x, and this middle piece is our f of x. And so what we want to show now is that the limit from the left and the limit from the right are the same of our functions, and then the function in between has to be the same. So before we do this algebraically, I want to show you guys the graph and what this thing looks like. So this is the graph of x squared sine of 1 over x. And so if we zoom in, because we're trying to find the limit as we approach 0, well, it looks like it's 0 just by zooming in a bunch. But you can see it's an oscillating function. And so the question is, we're going to bound it between two other functions, and we've bounded it between negative x squared and positive x squared. And so just by looking at this graph, we see that x squared is always larger than the function, and negative x squared is always less. Now if we zoom into the limit of x squared, it's definitely 0. So we can keep doing this for a while, and notice the smallness of the decimal points. We're 5 decimal points in, and as you can see, it's still bounded in between x squared and negative x squared. And again, we can do this forever, and it never goes outside of x squared or negative x squared. So now what we need to do is determine the limits. So then we write this as the limit as x approaches 0 of negative x squared, and we know that is 0. And we know the limit as x approaches 0 of positive x squared is also 0. And so now we've got all the pieces for our proof. We're going to need this piece, and this piece. So we're moving on to our proof. Here we go. So it's going to be an if-then statement. If these things are true, then our second piece will be true. So since negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared, and the limit as x approaches 0 of negative x squared is equal to 0, and the limit as x approaches 0 of positive x squared is equal to 0, then by the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. So again, the way this works is that we bounded it between two numbers, and then we just multiplied both sides to get our function back, and then we found the limit of the left function and the right function, and then for the proof to work, everything in yellow is the conditions to make it true. And then in pink is the theorem we're using, and then in blue is our answer. So the yellow is the if, this is the theorem, and then this is our conclusion. On your own now, I want you to try to use the squeeze theorem to show that the limit as x approaches 0 of x times sine of x is equal to 0. And yes, I know you can actually just plug this in and get an answer, but I want you to show it using the squeeze theorem. Alright, let's take a look. So before we actually solve this, I want to look at the graph and see if we can right away see a function we can bound it between. So this is what x times sine of x looks like, and doesn't really look like we can bound it between anything yet. But let's go ahead and take a look at the algebra and see what we can do. So by looking at the algebra, we are going to look at our function and try to bound it right away. So I'm going to take sine of x, and I'm going to bound it between 1 and negative 1. And then this doesn't look like my function yet, so I need to multiply everything by x. So I get negative x is less than or equal to x times sine of x, which is less than or equal to x. Now what this is saying is that x sine of x, that graph we just looked at, is always between positive x and negative x. So let's go ahead and take a look and see if that's true. So we're looking at this graph. The purple one right here, this is positive x, and then the gray is negative x. And as we can see, it's always in between positive x and negative x, no matter how far we zoom out. So now that we know for sure it's bounded, we're going to go ahead and find the limit of the left and the right. So then the limit as x approaches 0 of negative x is 0, and the limit as x approaches 0 of positive x is also 0. And now I have all my pieces. So since negative x is less than or equal to x times sine of x, which is less than or equal to x, and the limit as x approaches 0 of negative x is equal to 0, and the limit as x approaches 0 of positive x is equal to 0, then by the squeeze theorem, the limit as x approaches 0 of x times sine of x is equal to 0.